discussion about aligned representations. I on purpose didn't put the word multimodal yet, because today is really the day where we're talking about transformers. And before we go into multimodal transformers, I really want to take the time to talk about them in a way that at least I find more intuitive than a lot of the graphs that you will see in most papers. I really want to take the time to go into that, because after that, we'll build from that. So that's the objective today. We'll discuss a lot about different aspects of the transformer and also how to train them. We spent quite a bit of time about representation of words. You remember word to vec with the distributional hypothesis, and that was a good way to represent it. And but then we, in later part of, I think last week, we also started talking, but words have meanings, but they also, their meanings is related to the other word in the sentence. And really there's kind of two things. There's the meaning of the word when used in the sentence. That's one thing. And what is the overall meaning of the whole sentence? So I'm going to put that on hold for a second. And just the first question, how is the meaning of that related to the other? So how, without knowing yet about transformer, but based on the lecture from 1 or 2 weeks ago, what would be another approach to contextualize these? So recurrent neural network will be one. And as we talked about, there were the poor Elmo that was so good, but for so short amount of time, was the best in the world for a few months still. And that one was great. It was taking advantage of recurrent neural network, bidirectional. So here, left to right and right to left. And so the understanding of the representation here of the word is no more just the representation of the word, but the representation of the word after being contextualized. And for now, and for most of the discussion today, let's suppose that X1, X2, X3, X4, and X5 are already the word-to-vec representation. Okay, let's start somewhere. Okay, there are ways to train from scratch and all this, but for now, at least personally, it's easier for me to explain and also understand those models where the goal is not to start from scratch, but the goal is generally to contextualize, to add meaning, to improve the meaning. It's not to learn the meaning from scratch. Now, in later stages, you can train from scratch, but it's a lot easier to understand it as contextualizing. So what would be another way if you take computer vision with CNNs? You could also, because the problem with this is that if you have a sequence of 20 or 100, like LSTM are not good at being parallelized. So one of the issue with LSTM, and compare with what we're about to talk about, is that if I want to have this one, I have to go all the way there. There's no shortcut, there's no direct, there's not like I can easily put it in a GPU and I really sequentially need to go to the information. So for very efficient, convolution is really efficient. So you can run and in fact, this temporal convolution, 1D temporal convolution was one of the, there is a debate on who invented CNN, but the CMU version of it that came a little bit a few months before was about temporal convolution as one. So what is the issue here? Now you can go parallel, so this is great. But the way this information will be integrated, like the integration is all based on that dictionary of those convolution. The way information is merged as aggregated is always based on that dictionary that is learned during training. And at test time, it never changed. Once it's learned, the convolution, those templates, they stay the same. So the model has two issues. The one I just mentioned, that these are static, And the biggest of the issue is those are really local. It's the same thing with images. It's patches that only locally affect. And you need to create multiple layers to really get the long-range dependency. So this is why then self-attention can be, because they are parallel. They do the long-range dependency, and at test time, the way information is fused is dynamically decided based on what the inputs are. So all of the fusion is dynamically changing. By dynamically, it's just a fancy word for gating or attention. Like almost every time, not always, but almost every time someone talk about a model being dynamic, they may mean because it's like temporal. Some people use that term for that, or sequence or temporal, but dynamic in a learning or in the inference means that my weights are going to change at test time based on the input I have. That's what it means, dynamic. Okay, so self-attention, we're going to go slowly and we're going to go step by step. Any point of the time, like if you have a question, which you just ask me, my goal, what it is, I have a word, and I have already a word-to-vec embedding for each of them. And my goal is to get a better representation. And I can do two versions of it. One is the word, the meaning here is a better meaning from the original word, like you had a better meaning, or I can do it in a residual way, okay? So here at the high level is I have my meaning for every word, already word-to-vec, and then I will run it through my contextualizer. In one way is to just get a better meaning. So if I had an original X, in the same sense, it's to get a better meaning of it. The residual version of it, the residual version of it will say, I want you to contextualize, so the same thing, and find not just something that's better, but I also, if I put a residual node here, what's the difference? What becomes the goal of this compared to this one if there's no residual? What's the difference? Yeah, because I have this, the only thing I want is to learn the delta. What is it I need to change my X? What is it I need to change my X to get my X prime? Okay? And transformers are this way. Transformers are residual machine, but the core of it, the self-attention, could be used either way. Okay? But because I'm going to put a residual eventually, my current goal is to find what is it I can add to it, what is it I can add to this meaning that will improve it. But there's nothing that stops you other than empirically, it seems that the residual works better. But there's nothing that will stop you to remove that. And there's plenty of paper that tried with and without and different flavor of normalizing the data and all this. But intuitively, it works well because we know also in CNN, residual networks work really well. It also helps us to put many layers. As you remember, there was an issue with gradient. So this is something that you may not have realized, but transformers are usually a residual machine with the goal of saying, hey, what is it I can change based on my other one? So first, that was the first thing, but the self-attention I'm about to explain to you could be used in a non-residual way. So how do I get there? The idea is dynamically, I will decide how relevant the other words are to helping me better understand my word. So I have my word, and right now, how much this word, how important is it? How are the other words important for this word? Probably not the most important, but these two are definitely. And this one definitely change its meaning because of the other two. Okay, I do not like without the do not, very different. Okay, so dynamically, like depending on which input, like if I was reshuffling, like this like could have been in another sentence, I like it, then the other words have no change. There's nothing to change it. Really, well, that's what I mean by dynamically, is based on the input. Now I look at it, I'm like, oh, these words seems to be relevant to my word. And so I will adjust it. So dynamically. So what I want to do is let's start with the first word, and we're going to go to each of them. I want for this word, let's say for now, I'm just copying that same value here. Let's say I'm just copying. And I'm saying how much this word is relevant to my new delta. This is the delta, the thing I want to change to my meaning, so that it will eventually be a better meaning of that word. And yeah, definitely probably this, but since I'm going to do a connection, a skip connection, a residual connection, then probably not as much. But this attention will tell me how important each of these other words are in my meaning of that word. And then how do I aggregate? I'm not telling you yet how I'm going to compute them, but let's suppose I have those attention, then I will simply apply 30 minutes. I will simply do the usual that I do for attention, multiply the attention by each of these values, and then as a summation, as I did for most attention, simply adding that. So what this tell me is, okay, to really like, what is important here? I'm going to compute, let's say for now, magically, I'm going to compute an attention that tells me how important, how relevant this is, and then multiply by it and simply sum. And I will do this for every output. So for the do, I'm going to do the same. So it's the same 5 options. And then I have a new weight for each of them. So this weight, what does it say? It says how important for 2 is this option 1, okay? And how important for 2 is 2, how important for 2 the 3 is, how important for 2 the 4 is. And then I do the same thing, multiply and then sum. And so I do this for all of them like this. I just put it explicitly there. So for the light, I will also have an attention. I didn't show it explicitly, which would be alpha 4, alpha 4, 1. So how important for the word light, the word I is, and where do you start thinking the attention? This attention here, alpha 4, 3 is probably going to be really high because it's really relevant. When you have a light and a not, they really change each other's meaning. And so I want to have the alpha high. Now, what is really interesting also is that these X are in fact not going to be directly the X. And that's really cool. What it means is, because I in itself, my whole goal is to find how I can help the others. In fact, this X prime, like this whole thing is, how can I help the other? How can I contextualize it? What information in me would be potentially useful for others? That's what it is. And yes, it could be directly my word to vec, but maybe it is a projection of that word to vec in a different space. And in most transformer, it's a linear projection. So it's a linear projection. But I take my word to vec and I say, hey, and a person like a word like not would be, hey, I have quite a bit of power usually, and so it's going to be projected like, oh, sorry, I didn't put it where. And each of them will have it. I don't want to, but each of them. Sorry, I pressed too many clicks. It seems to be a delay today. So each of them will have their projection that says, hey, how should I change others? And so a word like not will have probably a strong one, and it will be knowing that in word-to-vec representation, like words that are negative usually are on the right of the word that are positive. Like, don't quote me. I mean, it's not like our word embedding goes from left to right when you're negative, but let's say, play with me for a second and say that all the word like, when they are becoming negative, they end up shift towards the right. So this embedding here is going to be shift towards the right. That's what it will be literally. That's a shift towards the right. The alpha are going to be like how important the shift to the right is to all the other words. That's what that vector is going to tell me. Now, I didn't tell you yet how to compute the alphas. So I'm going to tell you in a second. But now you know the purpose of those alphas are going to be to know how much shift to the right it is. So then how do you produce these alpha? Then you follow the same intuition. I will take my word, and now I will decouple it as a query or as a key. And it's arbitrary, they use those terms, but a query says, okay, and you do it for each of them. So you have a query and a key for each of them. I'm about to explain to you what the query and the key. And so the query says, hey, I have the word I, and I would like to know if in this sentence, there is any other word that may help me like better understand myself. And so I go ahead. So you have the query, the key, and this is called the values. So the values for this that you remember is a shift towards the right. So then here it does and says, hey, my word, I would like to know if any other word is also useful for me. And so the keys are to say, hey, if you think I can help you, that's what I look like. That's my key. This is what I look like. And the query is like, is there anybody who could help me? And then you do this check for all of them. So you're like, hey, is there anybody that can help me? Let me look myself. Let me look with that word 2. And you do it for the word 3, for the word 4, for the word 5. All of these are, in this case, is a decision we decided to use in most of them for efficiency. Just if you have 2 vectors and you want to know if they're similar or not, what's the easiest? Cosine similarity. But if they're already normalized, then it's a simple multiplication. So multiplying them to get the angle. So the alpha, really what they are these response to the query compared to all the keys. So A11 is this query for that word, check with the key. And then A12 is the same for the second word, A13 for the third word. And then you will do it again for the second row of way. So then the query for do is the linear projection of the word do, but being like, hey, is there anybody that can help me? Or is anybody that's relevant to me? That's another way. It's not like it's relevant, maybe proactively. And then the same way we will compare it with all of the others. And you do it for all of them. So I didn't do the animation for all of them, but you can imagine. So the word like, that query is specifically important. It's going to project. And it's a project, not just the word like, it's going to project in a space where words that can be affected by a negation is high. So the negation would probably maybe just project itself into a negation space. But the like will project itself into a space where word that can be affected by negation will be there. And so that when the 2 of them comes together, then it is going to be a very high alpha, a really high match. And then this will be multiplied by the not, and then you get your shift to the right for that value here. So this is the most important part of the transformer. After that, it's a bunch of engineering and everything. But this is, by a large margin, the most important part. The first is that my goal here, H, is really to find something that's better than the original because of the residual connection. I didn't plot it in that, but that's where my goal. The second thing is I take my X, I'm projecting it in a value that may be useful for others. Unlikely to be useful for me, but mostly for others. And then I say my query is like, hey, anybody relevant to me? So I know who I am. And then I'm going to transform myself in a way that based on, I mean, these weights are going to be trained. So when you ask, like, what is a transformer? These are the parameters. These are, in fact, the only parameters. And another thing is the parameters are tied. So that's why also transformers are, in a sense, very efficient, is that you can have it like 2000 sequence length, but the number of parameters are still going to be the equivalent of one token. Now, the processing over a 2000 versus a 200 will take more time, but the number of parameters is going to be the same. Yeah, there was a question. Yeah.
Question. So that V1 would be the information that's useful for X1, but for the other words. How is that different than attention 1, 3? And attention 1, 3 would be the weight of first word.
Yeah, so attention 1, 3 says is V3 a useful thing for X1? So alpha should be seen, it's usually between 0 and 1. While the V3 is the shift you want. So the V3, you kind of have a menu here. You have a menu of possible things that can be offered to you. So, I mean, V1 is offered to itself, but then V2 is offering it, V3 is offering. So it's offering some kind of change, each of them. So you could say this one is shifting to the right, this one is shifting a little bit in a direction. And then the alpha is there to decide, do I want that shift or not? Did I answer, or do you want to rephrase the question?
I guess that's a little bit confused on what you mean by shift, right?
Oh, okay. So X1, the X1 is already a representation of the word. Usually maybe word to vec like a 300. And my goal is to find, it's easier to do the word like. So the word like has already a meaning. But if you look at the other words in it, really like should not be like. Like should be negative like. It should be I don't like I hate, or I like. So in fact, like should be a lot closer. Once I added like the what is it? So x4 prime will be x4 plus h4. So that's the residual. So my h4 is sorry if you don't see it. Yeah, I just realized the angle. But yeah, so the h4, its whole goal, or more, I think it's a little bit easier to think about the x4 prime. The goal of the x4 prime is to be closer to the word hate than the original word, which is I like. So that's the goal of the change. So when I say a shift or a change, I'm thinking H4 needs to be the delta, the difference between hate and like. And I oversimplify it, but I said, let's say that I have a word space where every positive words is on the left and every negative is on the right. That's where the shift is. So when I meant V3 is a not, so not in itself may be somewhere in the space, but I really want the V3 to be the equivalent of a shift. Do you want to rephrase the question, or did it help?
That probably makes sense. Then essentially the attention weights represent how much each of the other words affect that shift to the right.
Almost, if it's attention. So that shift to the right is a menu, and all the other words will decide if they pick that item in the menu. So I think it's almost what you mentioned, but yeah. So the A13 says, does the word one wants that shift, that item? And does the A23, does the word two wants that item? And so, it's almost what you mentioned, but it's like, yeah, okay.
So regardless of the rank, we only learn like three weight vectors. That is WK.
Yeah, that's it.
Take 200 words to 1,000 words. You just learn three vectors.
Yeah. I will go in details. There's little, but 90% of the understanding of that algorithm is true. But then when you go into details, there's a few extra parameters here and there. But the core of a transformer are those three matrices. And they are linear also. So it's really just matrix multiplication. That's it, yeah.
So how the three base updated? So like are the losses summed up and then updated? Or then we do back propagation on that thing?
Yeah, I mean, you could train these in a supervised way. So, so you have a sentence and you know its sentiment, and so then the gradient will propagate, and the gradient will naturally try to move the query, the key, and the values in directions that does the right shift at the right time. That's kind of the idea, is the gradient is going to do that for you. But training of many of those transformers these days are done in a self-supervised manner, and I will tell about this. So BERT, so transformer came out, was great, but it was trained in a certain way, and then really soon after there was a self-supervised approach to train it. That's where BERT came in after that. Yeah, but yeah.
Just a clarification question. So the final representation goes to the next layer. It's actually equals to x3, for example, like the non-x3 plus like h3.
Yeah, it is. Yeah, I didn't put them at but there will be a link directly, and there will be a plus. So it will be x1 plus the h. Yeah.
That's what you mean by the residual.
The residual, or some people call it a skip connection or residual. Exactly. There's one more thing about normalizing these. There's a little bit of normalization, but these are more details. Yeah. Okay, so this is the most important, like this last figure. I'm going to show it again, but this is really the most important that you are training. And many times you have this as a one box, as if magically these were going to be computed. And that the only parameters are these, but these parameters are there because these are finding how to and it's a big challenge for these weight matrix, because it's one linear projection that is applied to all of my words. So somehow that linear projection is magically projecting any kind of word in their best query possible. So it's a lot of work for those queries, and a lot of work for the key, a lot of work for the values. So in practice, what they will do is say, what if you had many of them? So it's a little bit and so like I said, there's only one weight matrix for the query and one for the key and one for the value. In practice, you're going to have more than one. And more than one of these. So you will have just in fact a replication of the exact same thing, but like 10 times. And they're called fancy word multi-head, multiple head. Yeah, so multiple head just means, so the way I interpret it is that the query key and value, maybe there's one of those head that's just about negation and really good. But maybe there's another one that helps disambiguate words like it. Or maybe there's another one that's like gender or other aspect of grammar or contextualization. Now, at the end of the day, probably each head does a little bit of everything and like does a little bit more. But in my beautiful world that I can imagine, you could imagine one head that just really naturally just do everything so that negation is done the right way. Another head could be all about like it. I don't have it in the sentence, but you could imagine that the it relates to probably something I said earlier. And I want to disambiguate what it is. And so that pronoun needs to be disambiguated. So I will have multiple heads. And right now in many implementation, they're just linear projection. So what this is by default, each of them are probably going to be close to 0 or like not very strong, like because maybe for some heads, like the other words were not, like for negation, this word really doesn't need the negation head. But example, this word doesn't need the negation head, but it needs the head for the pronoun disambiguation. And so, and then you just sum them. So you just, and as you remember, the H is the increase, like whatever increase. So keeping it by default as 0 will be okay or close to 0. Yeah.
Understand like the significance of multiple heads, like how are the results for it? Like there'll be one weight, one piece of the weight for each of the heads.
Yeah.
But they'll be different because each of these weights are randomly initialized or like.
Yeah, there's been work on trying like to enforce those heads to be, I don't know, perpendicular to each other, they're in different space and all this. In reality, it seems, I mean, there's also approaches on how to initialize, but by default, if you randomly initialize, they're going to be in different part of the space. And the gradient comes in and it says, you need to fix it. I don't care who fixes it, but someone has to fix it. And the one that's closer to how it could fix it will go ahead and fix it and get more gradient. So if you believe in like optimization, you could imagine that that's what's happening. So by having enough of them and randomly, you hope there. Now, since then, there's like a lot of follow-up work to try to warm start things. So you maybe pre-train some on some, but like there's ways, or you could put a regularization term so that these are perpendicular. You can do all of this. In practice, random initialization seems to work well, also because you have so much data, but there's nothing that stops it from being redundant. So there is a good chance that some of it end up being redundant. And when you do visualization, sometimes you see it. Now, if you reduce the number of heads to be so small and you have so much data and you do computation for so long, at some point they're going to need to be different. Otherwise, your gradient is not gonna, your loss is not going to go down. So but yeah, random is a good start. Yeah. Mm-hmm.
Is it like the kernels in a convolutional layer? Are they similar? Like you need multi-heads and you need multiple kernels to capture different features?
Yeah, so the main difference between kernels and this one is their goals are similar. Like they want to learn the patterns that other pixels or other words could contextualize my words. In that sense, the difference is the convolution kernel does it once during learning, and the way they aggregate the neighbors is decided once when you decide the weight of the kernel. And during learning, But when it comes at test time, the weights are decided. You have many kernels, so you have different ways of aggregating information, but you have a predefined dictionary of how you can do it. The self-attention, its power is, imagine at test time, I decide a brand new kernel, its weight dynamically. So if you have to make the difference, the convolution will say there's a dictionary of way I can integrate information. The self-attention is power, is imagine if there was a CNN where the dictionary of the kernel or the value of the kernel weights were decided live at every iteration. That's the power of the self-attention, is like the kernel, as if the kernel are changed. So I know more, and so that's why I don't need 1,000 convolutional kernel anymore. I may be okay with 10, because as long as I can change, I can transform. Now you know transformers. I can transform my kernel dynamically to each input you give me. I still need a few multi-head just because it's linear projection, and this was decided linear projection for efficiency, because now I can run it really quickly to the GPU and it's very efficient. Multiplication is really well. So instead of trying to make these a lot more complex and having one magic kernel that's always changed, it says, why don't we simplify it and just allow for a few? But the question is a good one. Is the doing the same in a CNN, maybe if you have a very large number of kernels, maybe, but that they're not dynamic yet. Great question. Any other questions? Yes, one and then, yeah.
So like in your previous explanation, you said the kernels are updated dynamically for like the weights, I guess?
Yeah, the attention weights are like different. When I say dynamically, I mean, if the sentence, the words was different, then the kernel weights, but in our case, it's the attention weights, will be different. While the CNN, it doesn't have the attention itself, the exact principle of attention, but the way information is integrated is always the same way. While here, the way you integrate information is dependent on what the input was. Yeah.
That's because like the attention.
Oh, it's really because, so you could, it's not exactly that, but you could say in the CNN, these weights are learned once during training, and that's it. While in a transformer, these weights change every time I have a different input. So that's where the transformer, that's what it means. Transformer means the weighting factors, the way I convolute information, the way I integrate information, change every time I have different inputs. Yeah. Yeah.
So my question is that the alphas are actually not weights that are learned, right? It's the W's that are learned. Or
Yeah. So the way there's still parameters. I'm not saying it's not parametric, but yeah, the way I have parameters, but the parameters are parameters that allow me to compute the weights. That's why they're dynamic weights, those attention. So I have, instead of computing the weights itself, I compute a function that allows me to get the weights. Yeah. Great. This is it. I could probably stop the lecture now because this is the hardest part. Now we're just going to play with this. So this is just the same exact thing, but put in vector format. So in vector, so you have multiple heads. And then I can, there's one last thing. Sorry, I forgot. This is somewhat important because up to now, if I reshuffle the words, there's nothing that changes in it. Literally nothing, okay? So because if the word like was the first one and the word not was the last one, there would not be any difference in the current implementation I showed you. So they had to solve this, the people who, and that's the position embedding, exactly. So because if I reshuffle, it's exactly the same. So how do I handle it and sometimes the simplest is the better. Now, these days, they use something different. They will use sinus or something, sinus function, but the simplest way would be for every every word, in fact, put a one hot encoding of it. And you see, I on purpose fixed the ordering. So not was the third word. So it's really, so really literally the transformer has no clue. As long as you give it the right position embedding, you can reshuffle them. Now, in practice, you try to keep the ordering just for debugging purpose. So you will, if their sentence was, I do not like it, you have, but the I is the first word, do was the second word, not the third word, and then the fourth word and the fifth word. So this will give me the same as reshuffle version. Now, as we talk about, we're often gonna use, instead of the one hot, and then you will do an embedding of it. So the embedding is interesting, and it's about finding, what's the goal? It's similarity. We're about to do a similarity. And so you take the one hot, you project it, and then you do two choices. You sum or concatenate. If you sum, what do we know from multimodal fusion? If you sum, that means you put a lot of constraint on these two. This is the second one. You put a lot of constraint on these two because they need to be on the same space if you're going to sum them. Okay? So somehow you're forcing this WP to be in the same kind of weight space that the other. So often people will do concatenation also, but then there's many papers on concatenating, summing, making it in fact multiplying or making it a kernel. So there's a lot of extension, but the general idea is either you concatenate, in which case it's the word plus some position embedding, or if you sum it, what this is going to do is going to take the word and kind of shift its meaning a little bit. That's another way to think about it. And so you will do it for each of them like this. And in fact, the rest of the algorithm is exactly the same. So you take, instead of the word, is the word at a certain place in the sentence. Now, in reality, people, instead of absolute position in, they will like kind of a more relative position in. So there's been a lot of work on trying to change the position embedding to not be in an absolute position, but kind of a relative. And to do that, they will try different functions like very large variation or very fast variations. The idea is that absolute position is a little bit hard because if you have a very long sentence, or if you added one word in the middle or a little bit of words in the middle, how does it change the meaning? So a lot of times they will want more of a relative position. But for now, let's say the simple version, let's say absolute, it's absolute position that's encoded. And then if I put it in vector format, so I have my X, and from the X, I also get my position, and I get this as an input. I run it through my transformer, I get the delta. And as we talk about, there's query and multiple headed, and finally, the residual connection. So this is how, now the first paper, they didn't make it easy on us. This is the figure they showed us. And you see that, and you're like, what? And they emphasize so many things that seems really irrelevant, like all of these things, but really the core, and they had other figures. I'm not like saying this, but the core is really here. It's really about the contextualizing. But you can see in this figure, this is my residual add, and also a normalization. That's the main important one. And the input adds a position embedding. In the first version, it was a summation. So they were adding the position to the other. But as I mentioned, concatenating and others. And then they had a few extra things, a feed forward added on top as an extra thing. But the core of the core is this. So if you see those diagram, and many papers afterward show that diagram with a slight change and give it a new name. But the core is really what we just discussed. Okay. Cool. So how do you train this? That was a question a little bit earlier, like how do you train that? And that's the last part of the lecture today, is how can we perform many tasks with this? So for example, a transformer. So I have a transformer that I mentioned that from one embedding, let's say for now, for simplification, let's say that H1, so I should have put X1 prime, sorry. This should have been X1 prime, X2 prime, X3 prime, like after the residual, just for simplification. And then what you can do is, if you want to do a translation, you would like to take up to now what the translation has been done. Let's say I'm at the word je n'aime, and then you want to know what is the next word. So here's the, and I want to see if you understand query key, and that's the important one. So this is the source data. This is in English. I do not like it. I'm in the middle of a translation right now. Okay. And sorry, let's say this one I don't have yet. Like I'm searching for Y3. That's what I'm searching for, Y3. So I have je, and I want to know like what is Y3. So when I connect this to the previous representation, and I want to connect it to my decoder here, and do I connect this one as a query or as a key? Is this one a query or a key, or is it this one that should be a query or a key? And think about when we were using attention as part of image captioning. When we were doing attention as a part of image captioning, what is the query and which one is the key? I mean, there are two of them. So who thinks it's the query? Who thinks this one should be the query? Okay. Who thinks this one should be the query? Who thinks this should be the query? Seems that half the class didn't didn't commit. What is it? If it's not A or B, what is it? It's both, maybe. Oh yeah, that would have been a good one. Huh? Okay, so what it is I want to know what's the next word. So my query is how much I've done up to now is my query. How much of the translation I've done up to now is my query. And my key is going to be like which word in this are the most relevant to my new generation. So, and that's what we were doing in the image captioning, is like, okay, I generated up to these words. Let me look in the image which other objects are relevant so that I can generate the next word. So the way to put it is this is my query up to now, and I will generate, but the keys are coming from these. So the keys, you're going to all these options as keys, and then based on that, I will know how to generate. And then I will take that word, I will copy it in an autoregressive way, and then I will go ahead, and that will become my new query, and then I will look over all the words, which one is the most relevant, and I will generate my next word, and then I go. So this is a little bit complex, but I'm showing it because the first paper on transformer was a machine translation paper. So they took that transformer, and in fact, had 3 different transformers in it. They had the encoder transformer, they had the decoder transformer, the encoder decoder transformer. But the one thing I want to talk about the most was how do we train those transformers? How do we train these transformers? So I have 2 ways of training. I told you a sentence, and I said, don't worry, we're going to talk about the other one soon. I said, the sentence, every word has a better meaning because I contextualize it. That's what I show here. But I also sometimes want to have one meaning for the whole sentence. That's also sometimes what I want. The second thing that I want is these days, and that's something you know quite a bit, it's really popular, pre-training and fine-tuning. So when this came out, this was a new concept for NLP. It had been there for about 5 years in computer vision, but it was a new concept for NLP. So the idea was train a model on a large number of large data sets, and then what test time, I can easily, quickly adapt that model on a new domain, on a new data set. Fine-tuning will be. And I would like to do the fine-tuning with as little change to the original one as possible. That was also a goal of BERT. I'm about to introduce BERT. So BERT had 4 things. It jointly learned both better representation for each word, but also added this extra output, which is what is the summary of the sentence? And how do you do this? Do you remember in machine translation, how did we specify the start of a sentence? We just had a special token, start. So we'll do the same here. We'll put a special token as an input here. Will be kind of, I forgot the SCP or sentence, like a CLS, I think is these days. But yeah, I forgot we'll have it in a second. I'm blanking just now. But then the same network, I would like to use the same network for pre-training later on I will use it for pre-training and then for fine-tuning. The other things, which was just an addition, it's not needed when you train, or at least, but you will see it will help you to do the summarization, is that you learn not just the meaning of a sentence, but the meaning between 2 sentences, the relative meaning between 2 sentences. And finally, it models long-range dependency. Now, the last one is really about, because I have self-attention. I mean, the long-range dependency, self-attention, and I put a token, that's CLS, okay, for the whole sentence, and then a separator between the 2 sentences. Now, how do I train this efficiently? How do we train this with self-supervised? How do I train language? Yeah.
Except like the operator learns the related to sentence.
The goal of this one? The goal of this one is as a separator, primarily the separator. It will not, I don't think it learns, yeah, I think I misspoke about the learning the difference between the 2. It will learn what this is really is, yeah, sorry for saying it's comparing 2 sentences, although you can fine-tune it to do that. By default, what this is going to do, it's a contextualization machine. So really what it is it's going to take the meaning of these words into the context of that previous sentence. So that is a better definition of what it's doing. The saying about comparing, it is not by default how a transformer behaves. The behavior of a transformer is all about contextualization. So thank you for clarifying this. It is really about the meaning of here will be not just because of that sentence, but because of the previous sentence as well. So that's the main thing it does. But yeah, how do we train with self-supervised? How do we do it for word2vec? Distributional hypothesis. That's exactly how they train it here. So the main way to train it, and now these days, distribution hypothesis is known as masking, but this is what this is like I will mask a few words, and I know it's real words, so I know the ground truth because I know the sentence. And so what is the loss here? Just comparison. You compare the embedding of like, so it could be all the way to one hot embedding. It could be like you could force this all the way to a one hot embedding of which word you think it's output, or you could train it and say everything starts with word to vec. So really I'm going from input word to vec to the word to vec, and so I'm predicting the word to vec output. But these days a lot of those BERT are trained end to end. So like we don't even have a initialization of word to vec. It's really just a one hot embedding, and then it's predicting a one hot embedding at the output as well. But I don't know, how do I know that how do I get a meaning of the whole sentence? Huh? Yeah, okay, so so the loss is, one term of the loss is how well I succeeded on the mask. And then the second part of it is, as was just mentioned, is the next sentence the right one, or should this one come after this one? And you could do this different version that has been proposed, but they could be just flipping the order. In one case it is, in one case it's not, or it could be from randomly other sentences that are not seen in the corpus as the next one. But their goal here, by forcing this token to know if this sentence is the next to this one, it should be a summary of the whole sentence, of both of them, in fact. But if what we will do as a test time, what's really cool is, although I train it into this next, I can still use it at test time and don't use the second part at all. Just use one sentence, and this will end up embedding or learning the meaning of the sentence. So, but this is the original BERT. There's been a lot of extension of finding other way of doing self-supervised learning. This was just one that they thought about, which is a good one to start with. So, but what's nice with this is, the training data is easy because you just get any data that has at least kind of continuation. It cannot be just a bunch of sentences. That's not sufficient. It could be data on Wikipedia. It could be books. It could be a mix of everything. And then there is this thing about how to different sentence. And so I'm going to show you this. So how do I know that this word is part of sentence 1 and this word is part of sentence 2? There's two kind of ideology or way of philosophy behind it. One is that the separator was sufficient to tell the model that this word is part of the next sentence. But that's putting a lot of pressure on that token. So instead of that, what usually people do is that there will be a position embedding, a one hot of the word, but also we'll have maybe a 0, 1 of like, is it the first or second sentences? So that way, every word will have embedded in it like its meaning and the position of that, and then is it part of the first or second sentence? So for fine-tuning, what's really cool is that once I train this, and maybe I will stop, maybe I will finish this at the next lecture because I know your brain is probably about to be fried. So I'm going to give you a preview of it and we'll review it again on Tuesday. But yeah, so once you train this for it, then you can use it at test time. And what's really nice is that if I want to use it for sentiment analysis, I don't really need to change anything there by default. At least if I believe that my data was trained well enough, I can probably get only one layer neural network or one or two plus a softmax. Or if I really believe that this is enough by itself, I could just put a softmax over my label. But you probably need about one layer here. But the idea is really you don't need to change it, hopefully, on your test time on your data. Now in practice, you do see both, like some people will say you should change and fine tune on your data. And then as you're going to see, even in some papers you probably read, now they're, instead of not fine tuning, which was the way we were calling it, now they got another word for it. It's like we freeze this. So you're freezing it is just a fancy way for saying, I'm not fine tuning it, but now it became a verb. So I'm freezing it. It's like, it's a new thing. But mostly what it means is I'm not fine tuning it. So that's just what it means. And if we have a label for each token, then you can learn a classifier that knows, and that maybe those weights will be tied usually. Like it's the same classifier for every word. Or you could make it more fancy, but that's, for example, a good way to do it. And how to compare, that one was a little bit fancy. Like if you want to extract data, like question answering, so you want to know where in my text is the answer to my question. So the question can be embedded here. And then the fancy thing they did is they compare the output with the token start. And that gave them the start of when this is, so here you'll have the whole text. So here you have the question, and here you have all the text. Okay? All the text will be here. And then the only idea is like, which of these words is really looking like a start token? And you do the same for the end token that way, and that will find you the start and the end time of the, so I will stop there. We'll revise that a little bit after a fresh start on Tuesday. You can look at the slides a little bit, start looking at this. But we'll look at a lot more transformers. So there's a lot more multimodal transformer and all this. But now you know why they're called transformer. The dynamic, it's not convolution kernels, but the dynamic weights on that. Okay, thank you.